how about the middle wired negative gradient? I can set generalize for the like layer 2. I can say negative gradient, negative partial error with respect to weight J to K. So J is input layer, K is output layer. So in that case, you can see 4 examples, 1 to 1, 1 to 0, 0 to 1, or to 0. So they are J to K. Because the layer is also mentioned here as 2. So for the layer 2. So you can rewrite this one. Error equation cannot be changed. So error is still 1/2 sigma I Ti minus I layer 3 square. But now respect to different weights. So second layer is weight. In this case, you are going to think about one example of Y03 is here in the green color. Then let's think about weight 01 layer 2 is this wire. They are never related. So in that case, you can think about if we use K for the input level, only weight final destination K will be related. So for K is 0, only weight layer 2, 1 to 0, and weight layer 2, 0 to 0 are related. So only K matters. The reason we were talking about this one because we do not like sigma. So because of this, we can take out the sigma because we care only K. So you don't worry about the different input level. Only input level K. That means sigma summation, which is missing here. Summation is gone. So I can rewrite as T sub K. That means input level is K minus Y sub K 3 square. Then we can derivative. So 2 is out. Then after you write everything, then partial of inside. So it's a chain rule. Then if you simplify, we're going to get finally positive T sub K minus Y sub K layer 3 times partial of Y sub layer 3 respect to weight J to K layer 2. We're still in the layer 2 way. Let's think about Y sub K layer 3. Yes, same thing. We can rewrite as X sub K layer 3 times Y sub KK layer 3. This is a layer 3, final layer 1. So you don't need to worry about the summation. So we can rewrite that as X sub K layer 3 times weight sub KK K to K layer 3 with respect to weight JK layer 2, this part. Actually, weight K to K is independent to any weight in those layer 2. So you can care only the first one, X in layer 3, because they are independent. They are not related. Independent, partial, derivative of independent to independent is 0. So we can rewrite this one to this way. So from here, the top to the second one, you are going to do the product rule. So X, partial X to weight JK times weight KK plus partial weight kk respect to weight jk times xk layer 3. So second part is 0. So first part is left. So you can see the weight k2k layer 3 times partial xk layer 3 respect to weight j2k layer 2. Then you can think about how to simplify this one, this partial, how to do. Actually, xk layer 3. Let's think about here. There's one example. How about x1 layer 3? So I assume k is 1 in this example. Is the result of the logistic function or transfer function of this perceptron of input of y k layer 2. Is it good? So if I want to get derivative of x1 layer 3, that means derivative of f when input is y1 layer 2. And derivative of y1 layer 2 is derivative of the big one times chain rule. Times chain rule, that means y1 layer 2's prime. So I can think about here. So this is the chain rule part. Y1 layer 2 prime is this red color. Then the outer one prime, we can write like this way. When the output is x k layer 3, the derivative of the transfer function or activation function. But activation function we already calculated as our warm-up. So if the activation function is a regular one, like 1 over 1 plus e negative x, we can use a transfer from, we can use the warm-up 1's final answer as y times 1 minus y. So in this case, y is x1 layer 3. So you can rewrite as xk layer 3 times 1 minus xk layer 3. Now let's simplify a little bit more. So you know that this one you can rewrite as xk layer 3 times 1 minus xk layer 3. It depends on what is the transfer function, activation function. So just know that, but we are going to keep this format. Let's think about some more if I can simplify more. Now I have y partial yk layer 2 respect to weight jk layer 2. If you see this situation, that is those two wires in the red color on the big picture. Yk layer 2 is a sum of A plus B, A and B. So you can think about the relation between A part and B part. Actually, A is not dependent on B. They are totally separate. They are independent. So in that case, we can say partial yk layer 2 does not care xj layer 2 times weight kk layer 2 part. That means we can take out the summation again. So I can rewrite this one, this partial, final partial, to just to the corresponding weight. So This means if the the wire is like a 1, 0, you don't need to care about 0, 0 part when you go to the y02. So you can rewrite without summation, weight, input, output, layers matching. Only matching part we care. Everything else, partial is 0. So you can rewrite partial weight j2k layer 2 times xj layer 2. So that means if weight is 1 to 0, only x1 is cared. Only part A or part B is cared. If you understood up to here. Now, almost done. When you do the product rule on the right side, partial same is 1. But when you have constant, because x is kind of input for this wire, so not this wire. So x is input, then y is scale factor. They are not relevant to each other. So partial is 0, derivative is 0. So you can simplify as xj layer 2. So instead of the whole partial, you can just write xj layer 2. So this j is the input layer. Then the other part are all care about the output layer only. You can see this one. So we can generalize in the back propagation diagram. We can have xj2 from the forward feeding, like if j is 1, we can say x1 layer 2. This is when j is 1 case. The other whole part, like k, output 1, if k is also 1, we can say this node, this E node, so if k is also 1, you can write this whole into this node. So it's a back propagation network. At the previous page example, we filled out the final node, final E node. You can say also this E node as E input level 1, layer 4, then, or final layer. Then the second part, you can write as this whole thing, T1 minus Y1 layer times weight 1 layer 3 times derivative of the activation function at x1 layer 3. That's what E1 layer 3 node will have. So you are going to use those two. After you are done forward feeding, you are going to build a back propagation network by calculating with the result from the forward feeding network. Then the direction is now backward. You are going to update the final node, then calculate the partial and get the E node, then keep going back, the backward. So you are going to store all those, I'm gonna use a different color, the blue color, all those negative derivative and E node, not arrow node. This one is just the E node. It's different from arrow, but related to arrow. That's why the name is E. E node values and build this back propagation network. After you build this back propagation network, you can use both together to make the network better.